previous lecture we talked about sliding window protocol. We recapped the concept of sliding window protocol and then we deep down into go back N protocol fundamentals. Now after looking into the fundamentals of go back N protocol, let us try to understand the working of this go back N protocol in a step by step manner and with the help of few examples. So when we look into the working of go back N protocol, let us say let us try to see what is happening with the communication system at the sender's side. So sender side, let us say in this we are talking about GB4, that means the window size or N is 4. So here sender, as I have already told you in the previous lecture, is going to maintain a window of size N. Here N is 4. So sender is going to maintain a window of size 4. So that essentially means it can send up to N, or here in this example it can send up to 4 unacknowledged packets. Now each transmitted packet has a timer. If the corresponding acknowledgement is received, the window is being slided forward. If the timeout occurs, maybe it is a missing packet or it is a missing acknowledgement. In both the cases, the sender retransmits that packet and all the subsequent ones in the window. That is what we can say the specialty of or the characteristics of go back N is. So if it is go back 3, then that 3 and 4 both are going to be kind of repeated. So if the timeout occurs in case of the packet is not being received or the corresponding acknowledgement is not being received at the sender's end, the sender is going to retransmit that packet and all the subsequent packets in the window. That is what kind of is expected from the sender side. Moving on to the receiver side, I have already told you the receiver side is going to maintain a window size of 1 because it is going to accept only the packet which it is expecting. If an unexpected packet is going to kind of going to be received at the receiver side, it is going to discard it. If the correct packet arrives, it is the responsibility of the receiver's side to send an acknowledgement and moves to the next expected sequence number. If an out of order packet arrives, so for example 2 is missed and then 3 is arrived while 2 was expected at the receiver's end because 1 was already there. So 3 here is actually out of order, so it is going to be discarded and the kind of receiver is going to resend ACK1 because this 1 was the last correctly received packet. Now this this whole scenario we can understand with the help of this figure. So here we have the receiver's side on which you can see a separate window for one packet or a window of size 1 we can say. Here let us say we have a bigger window size which is kind of having 6 0 1 2 3 4 and kind of 5 packets. So 0 1 2 3 and let us say the window size, the initial window size at the kind of sender's size is 4. So sender is going to send 0 1 2 and 3 4 packets without waiting for the acknowledgements, and for every packet it is going to be a timer. So it sends 0, a timer starts it sends 1, it is also kept track of by using a timer. So now here if you can see in this figure, 0 is being acknowledged, so is 1, 1 is also being acknowledged, but 2 is kind of somehow is lost, it is not being received at the receiver's end, and you can see there is lost is being written. But S2 is lost, but 3 is going to be or 3 is received at the receiver end, but 3 is something which is not being expected at the receiver's end, so it is going to discard it and it will send ACK1 again, so that all the subsequent ones can be kind of resent, even if there are kind of 4 and 5 other packets, it will be discarded at the receiver's end. And if you can see the sliding procedure of the window at the sender's end, so 0 is fine, then 1 is fine, then this window keep on sliding, so that 0 and 1 are fine, but 2 is stuck. So whenever kind of a packet is missing or an acknowledgement is not there, then in that case it is the window will not be kind of slided. So this way this is going to happen, and it will kind of a window will keep on sliding as the correct packets are received at the receiver's end, and the acknowledgement is also being correctly received at the sender's end. So this is what the procedure of this go back N protocol is. And please notice at the right side there are kind of windows for windows of size 1. Now here this is another figure in which we have taken a window size of again 4. So 0, 1, 2, 3, and let us see how this window is being slided. So frame 0 and then frame 1 are being sent. Now ACK2 is sent. So ACK2, that means the frame till frame 1 it is it has been correctly received, and so at the receiver end you can see the darkened window or darkened frames. Then frame 2 is being sent but is lost. Frame 3 is being sent, but it is kind of it is not the expected frame. So this will be kind of discarded, and then it is going to again ask for the frame 2 and frame 3. So this is going to happen if we talk about this go back N. Now in my previous lecture I have already told you that there is a very strong relationship between window size and the sequence number. So window size and sequence number in this sliding window protocol, let us say go back N, or even selective repeat, which we are going to cover in our upcoming lectures, are closely related. So there is a relation between window size and sequence numbers. So this window size actually determines how many packets the sender can transmit without needing an acknowledgement. So basically we can say it is like a limit on how much data can be sent before the sender has to stop and wait for the communication. And that is why I have told you that in case of this window size becoming 1 or window size reducing to 1, this is going to be a stop and wait protocol. And I have already told you that sequence numbers are used sequence numbers are used to label the packets so that receivers know that they are arriving in order and can detect any missing packets. So for example sequence numbers are 0, 1, 2, 3. So if it is having 0 and 1 and then it is having 3, so the receiver will be able to figure out that kind of 2 is missing. Now the window size should be smaller than or equals to the range of available sequence number. Now how many sequence numbers will be available? That is kind of 2 to the power n minus 1 that we have already seen. Now what will happen if the window size is too large as compared to the sequence number range? The receiver might get confused because the same sequence number could be reused before the first one is the first one is acknowledged, and thus it will be hard to know if the packet is altogether a new packet or it is going to be a duplicate packet which is already received. Now relationship between window size and sequence number is given by a formula which we call is window size size of the window at the sender, which is WS, plus WR, which is the WR is the receiver window size, must the sum total of WS and WR must be less than equals to ASN, where ASN is the available sequence number. Or in go back N we can say that this WR is going to be fixed to 1, that we have seen already. So ASN or we can say WS, which is the sender window size plus 1, must be less than equals to ASN, which is the available sequence number, because WR is equals to 1 when we talk about go back N protocol. So, minimum sequence number required in go back N is going to be N plus 1, and obviously the bits required for this for this in go back N protocol will be log of N plus 1, and that is ceiling of log of N plus 1, and log here is log with base 2. Now, why this extra 1 is required? This extra 1 is required in order to avoid the problem of duplicate packets. How this extra 1 is going to help us in avoiding the problem of duplicate packets, we will be seeing with an upcoming example. Now, let us say we take an example of GB4. We have already seen such numbers with go back N. So, sender window size is 4. So, therefore, we require a minimum 4 sequence number to label each packet in the window. Now, suppose the receiver has received all the packets means so 4 is 0, 1, 2 and 3 which are sent by the sender, and hence now it is waiting for packet number 0 again, and we cannot use 4 here because we have only 4 sequence and number available send is equals to 4, and we have already used 1 0. So, we can go till 3 only, we cannot move to 4, that is for sure. Now, suppose that a cumulative acknowledgement for the above 4 packets is lost in the network. Now, cumulative acknowledgement, when I have in the previous lecture I have told you that one acknowledgement for all the packets received. So, for example, acknowledgement 4 is the packet acknowledgement 4 is the acknowledgement for all packets received till that point, which are 0, 1, 2, 3 and so on and so forth. On the sender side, now let us say this cumulative, there is a system of cumulative acknowledgement, not the individual acknowledgement ones. The above 4 packets and the cumulative acknowledgement for the above 4 packets is lost in the network. On the sender side, there will be a timeout for 0, there will be a timeout for 1, there will be a timeout for 2 and 3, and hence all the packets, all the 4 packets will be transmitted again, because on the sender side there is a separate timeout for each packet. Now, what is the problem here? The problem now here is the receiver is waiting for the new set of packets, because it has sent that acknowledgement for all the 4 packets, but the acknowledgement went missing in between. So, now receiver is expecting 0, 1, 2, 3, 4, the newer set of 0, 1, 2, 3, 4. So, which should have started from 0, but now what the sender is sending? Sender is sending the previous 0, 1, 2, 3, 4 because it has not received acknowledgement for the previous set of frames. So, sender will send the previous set, and now it will receive the duplicate copies, which is the receiver will receive the duplicate copies of the previously accepted packets. Now, this is a problem. This is kind of at the receiver's end, this is going to create a huge confusion that whether this is a new set or kind of renewed sequence numbers used for the new set of packets, or it is kind of a duplicate one. So, in order to avoid this, we need one extra sequence number. This was the sequence number which I was talking about when we looked into the number of bits which are log of n plus 1 kind of. So, with this one extra sequence number, the receiver could easily reject all the duplicate packets which were starting from 0, because now it will be waiting for the packet number 4. So, we have added an extra sequence number now, which earlier we were not kind of which we not have added in the earlier set, which was 0, 1, 2, 3, 4. Now, we have added 0, 1, 2, 3 packet number 4 also. So, we have added an extra sequence number now. So, here you can visualize this whole thing with the help of an figure here which is given on the screen. So, we have go back 4, which is a window size of 4, and at the receiver's end the window size is 1. So, 0, 1, 2, 3 are being sent. ACK4 you can see is kind of lost, and then this is going to send 0, 1, 2, 3 again, which are kind of duplicate packets received at the receiver's end, and then these are supposed to be, or these are kind of should be identified as the duplicate ones and should be discarded. This is a situation which is happening without kind of an extra sequence number. Now, let us say we have given an extra sequence number, try out with one extra sequence number, which is now 0, 1, 2, 3 and 4 also. So, for example, 0, 1, 2, 3, again 4 is being kind of lost. So, 0, 1, 2, 3 when kind of sent again, it will be automatically kind of we can say discarded by the receiver, and receiver will be able to identify that these are the kind of we can say duplicate ones which are which have been already kind of sent once. This is a repeat set of packets. So, that one extra sequence number is going to kind of save us from this identification, or from is going to save the receiver from this goof up of having the duplicate packets, identification of duplicate packets we can say. So, it is clear that why are we looking for that extra 1 bit in go back N protocol. Looking into the advantages of go back N protocol, we can say yes, it is simple to implement and also effective for reliable communication, because acknowledgement is expected at the sender's end, and if acknowledgement is not being received, sender is going to retransmit it. So, it is obviously going to give us a better performance than the stop and wait protocol for error free, or we can say low error network. If our error network is on a higher side or on a higher frequency of errors, then this go back N, because all the subsequent packets will be retransmission is huge here. Even if kind of one particular packet goes missing, or one particular acknowledgement goes missing in case of independent ones. So, because of huge repetition, in case of low error networks this is fine, but in case of high error networks that could be a kind of a problem. Looking into the other side, the disadvantages, I have already told you it is going to be an inefficient protocol if errors are frequent, because multiple frames might need to be transmit unnecessarily, and that too again and again, and because of this the ultimate result is the bandwidth is going to be wasted due to redundant transmission. Now, also let us try to understand the scenario that when we talk about these efficiency things, what will be the efficiency if we are kind of assuming the processing delay, queuing delay, transmission delay of acknowledgements is not 0. So, in this situation efficiency actually is given by a formula which says N multiplied by useful time, the time which is being used, divided by the total time. So, useful time here is the T based T of T, and the total time if we see is T of T plus 2 into T of P because of this kind of propagation, plus P of R plus P of Q, plus the time which is kind of we can say utilized for acknowledgement. Propagation of acknowledgement is also there. So, T of T ACK is also there. So, transmission delay of the sender side which is T of T, propagation delay PR is the processing delay, PQ is the queuing delay, and T of T ACK is the transmission delay of the acknowledgement. So, with when we are going to sum up all these values, then we are going to have the total time. What are the values we are going to have? Transmission delay of the sender size, then there is propagation, could be a delay, some delay at the receiver send some processing, then there could be a queuing delay, multiple packets or multiple acknowledgements in the queue, then the transmission delay of acknowledgement also there. So, efficiency when we talk about is going to be kind of a sum of uh, uh, a sum of all these times has to be taken into consideration when we talk about the total time. So, n into useful time divided by total time is going to be the efficiency. Now, bandwidth, if we talk about effective bandwidth or throughput, is efficiency into bandwidth. So, efficiency, if we denote this efficiency by n divided by 1 plus 2a and bandwidth by b. So, here we have the total the formula converting up into n divided by 1 plus 2a multiplied by b, which is the bandwidth, and this is going to give us effective bandwidth, or the another term for this effective bandwidth is throughput also. Now, this was the concept of go back n protocol. Go back n, as we have seen the examples of go back 4 or maybe go back 5. Now, let us try to understand the concept of the upcoming one, which is selective repeat. Now, selective repeat is also a part of automatic repeat request, but when we say selective repeat, within the selective repeat concept, the sender sends a number of frame is specified by a window size. Obviously, without the need to wait for the individual acknowledgement from the receiver, as we understood in go back and ARQ. Now, here receiver is kind of allowed to selectively reject a single frame which may be retransmitted alone. What happened in go back n, the receiver was not allowed to select for selective rejection. That means, if 3 is not received or the packet number 3 is not received, then 3 and 4 both are needed to be retransmitted. So, that was giving us kind of a wastage in bandwidth. So, here receiver is allowed, or receiver may selectively reject a single frame, and that single frame is needed to be retransmitted alone. So, this idea or this concept of selective repeat is in contrast with other forms of ARQ, which must send every frame from that point again, and which is go back n. Here the receiver also accepts out of order frames and buffer them. In the previous one, which was the go back n, receiver is going to discard all the out of order frames. Here out of order frames are welcomed and buffered. The sender individually retransmits the frame that have timed out, that means for which the acknowledgement has not been received. So, now with this just the looking into the concept of go back and we have completely understood. Now, selective repeat, which one is to be used and when? Should we use go back and, or should we use selective repeats, because both of them are having their own pros and cons. So, if errors are low, we might use go back n, but if errors are high, so in order to reduce the frequency of retransmission, we might use selective repeat. That is a better idea. If and this decision also depends on the bandwidth. If bandwidth is cheap, we might use go back n, and if bandwidth is costly, we might use selective repeat. Now, after making this or even in order to make this decision, we need to look into the differences of ARQ versus a selective repeat. So, go back and ARQ, when we talk about, all the subsequent frames must be sent again if the frame is corrupted or lost. In selective repeat, however, we are going to cover selective repeat in along with the help of examples in our upcoming lectures, but let us try to understand, let us try to grasp the concept here. So, selective repeat ARQ, when we talk about only the frame that has been corrupted or lost is sent again. So, selective repeat. While your go back N ARQ wastes a lot of bandwidth in case of higher rate, there is less bandwidth loss in case of selective repeat. Go back N is actually, we can say, it is less complicated, while maintaining a record of whatever frames have been received, whichever frames have been received, whichever is not being received, it requires sorting and searching. So, selective repeat is actually kind of more difficult, and it also requires more storage, because buffering facility is also given to the receivers end. Then here, if we talk about go back N, it does not require any sorting kind of thing. So, sorting is done when we talk about selective repeat, in order to ensure that the frames are in correct order, or we can say in order to identify the missing frames. In case of large windows, if there are so many frames, then sorting is required in order to identify that which all particular frames have not been kind of received at the kind of receiver's end, so that demand of selective repetition is being kind of we can say raised. Now, searching also is not required when we talk about go back N, while search is carried out in order to look for the kind of frames, and go back N, we can say, is used more frequently, but because of the complications of your selective repeat, it is used kind of less frequently. So, it entirely depends upon the usage, or entirely depends upon the application, that which sliding window protocol we are going to use. Although we kind of need to look into the examples of go back, and that I will be covering in my upcoming lecture. Here we have looked into the total working of go back N protocol, and we have looked into the examples also, more about selective repeat protocol in upcoming lectures. Here is a list of references which is being used for the preparation of lecture. I hope you have enjoyed this one. I will see you in the next. Till then, take care. Goodbye.